Okay, so any questions on just AP format 1 or 2? I'd like to go over some things. Just FYI on that again. It's just about exposing us to some more things. It's not meant to shatter your beliefs and make you doubt yourself. I told you which ones you should have kind of circled in the first place. The ones like I need to understand these, but other ones, it's always nice to just get more information. So anything 1 or 2, there's a few that definitely I could see you wanting and need to kind of go through once. Pin hitting nothing? I had to like cut last hour off.
You all.
Oh, Evelyn. What, number 5 on format 1? Okay.
Oh, yeah, that's exactly what I was going to
I had that one circled.
Well, why doesn't anyone talk?
I didn't know
Because I
that was
was-
a circle and we were supposed to know how to do
No,
it.
no, it's not. But it's something that I think it's good to see. All right, here we go. It says an excess of concentrated ammonia, so you should know that it's NH3, is added to freshly precipitated copper 2 hydroxide. Don't get confused by that. All that means is that that's a solid. So if you're like, oh, freshly squeezed? No, freshly precipitated, it's just a solid. All right, and that's all it says, I believe. Now, you got to fill in the blanks a little bit. Please just take this for what it's worth. When you are given something that's excess like this, and you have a transition metal, these are the 2 keys of this, you are making a complex ion. This is very rare for us, not rare in general, but rare for us. So if you don't have one, you got to make it. If you have one, you have a complex ion and it's added like to acid, acid's going to break it apart, and the metal and the ligand will actually separate. But in this case, you're going to make it. So this is going to literally come in here, sever off anything that was there, and it will become the new connection, the new ligand. So, translation. I now have, I'm not done with that yet, a ligand connected to my copper. What was our rule? The number of ligands attached equals to what? What about the charge? Double the charge. So this is 2 plus, and even if it isn't 2 plus, the copper part is 2 plus, I should have 4. Why is it still going to be a 2 plus? Because ammonia is neutral. The thing I want to make sure I said today, because equation writing is difficult, is if you have a positive ion, what must you have? What else must you have? You have to have a negative. You always have to have partners. If I have a positive ion floating around in a solution, there has to be a negative ion there somewhere. So who's the negative ion? The OH minus. And then we balance. And if you just look, oh, I have 2 OHs, so I need 2 OHs. And I have an NH3, and there's 4 of them, so there's 4 N's, 4 N's. And that one is done. The follow-up question is something to the effect of what type of reaction is this? Is that good enough to say? I can't find my sheet. So,
It says ascribe the effect of that acid have the products of it.
okay, on the product. So what you would do is you're creating a complex ion. That's what you're doing, ultimately. Okay? So you're making a complex ion. That's the effect. This would not happen if it wasn't in excess. Excess means that you have more. With complex ions, I hope we're putting on potentially more than it could ever hold. Like we're breaking octets. We're doing more than usual. Maybe not in this case, but we could. So think of that like it's excess. We're just flooding it. So that's when maybe your mind can go to a ligand and a complex ion. Again, if it does great. If it doesn't, it's not going to be the end of the world. Oh, that's right. Anything else? Yeah. 4 on 2. Okay. Yep. And I believe I might have made a mistake in the. We'll fix it if I did. Okay. So. This is confusing, and I'm actually going to be a quote-unquote good test taker and show you how I could have figured this out potentially if I didn't know all the information. So a piece of iron is added to a solution of iron 3 sulfate, and this is where I made a mistake on the answer key. I think I just put +1. Why are they broken apart? What do I know? What does it tell me in the problem? Solution. Well, I don't know if it's soluble. It's telling me it's a solution. Stop being so difficult if that's what you're doing yourself. Like, it's telling you. You don't need to prove it again. Like, it's good. Here's the problem. I don't know what's happening. Like, can't kick itself out, right? That doesn't work. So something else is going on. The minute I look at something like, none of this makes sense, and maybe it's not the normal single replacement, double replacement. Maybe there's something more to this. So I always maybe look down and think about follow-up questions sometimes, if I'm really stuck. And the follow-up questions on this, whenever you have to write in a reaction, sometimes really can help you. And it says, how many electrons in total are transferred in this reaction? If I'm talking about transferring electrons, what type of reaction is that? Those are redox. So someone has to gain and someone has to lose, right? Okay, if I think of redox, I think of electrochemical cells, and those things that are sticking in those cells are metal electrodes, right? Metal electrodes. The only metal is here and here, right? So this is 0, this is 3 plus. I don't expect that you know this, but I bet more of you know this than you think. What is the other charge that iron can have? It's 2. You've done this enough. Like, anybody know what the 2 lead ones are? Just curious. 4 and 2. Yeah. Copper's 1 and 2. Gold's 2 and 3. Like, sometimes you're like, wait a minute. Oh my God, I can't believe I knew that. So if I had a 2, does that satisfy? I'm not expecting you to know all this, but if you had some of this given to you, again, you got to remember, this is probably further than you have to reach now. But if you're understanding some of this, you're going to be great. From this to this, is that oxidation or reduction? Just look at the charge. It's oxidation. Oil involves loss, so I'm losing electrons. Or I just think of oxidation gains in my charge. Better way to put it, though, this one's always the one that's easier. You're reducing your charge, literally reducing the number. So that's reducing. This is oxidation. So what's my other partner? If I have a 2 plus there, what must be the negative? The sulfate. Now, you are probably not going to have to do too many net ionic equations, but if you can even get close to this, and then it's not asking for a net ionic, you're going to even be stronger. So what can I do? There's a couple things. I need to cross these out. I know this looks really odd. Very odd. And then I need to balance it. Well, it's already balanced. Well, not really. I have 2 FEs, I only 1 FE. The main thing I would do is actually do the charges. I have 3 plus and 2 plus. So if I put a 3 here and a 2 here, I balance the charges, and voila, I balance the FEs. I am not expecting that you can totally just from scratch get the whole idea of F plus FE 3 plus gives you FE 2 plus. That's not the goal. We try to understand as much as we can. So how many electrons in total are transferred? All you got to do, if you balance this out, you just have to figure out in one of the 2 brackets that I made. So there's one that's much easier than the other. If I just go from the FE one, how many electrons are transferred? Wouldn't it just be 2? Well, how about the other way? It's got to work the other way. It just has to. So it's 2 electrons. Because this thing's balanced. So it's got to be good. So 2 electrons are transferred. Okay. If you have some other questions, we'll hopefully get to them. I'm not going through this whole problem. What you have in front of you. What you have in front of you is not extra work. Oh my gosh, it's not extra work. It is from 2016, though, just last year. What I want to do is a little bit of a lab problem for you. So we're only going to do about half of this. I am constantly reminded and frustrated at myself when I see students struggling on things that are not that challenging of actual work, but they get confused by a lot of the images and wording and all that good stuff. So I want to go through a lab problem. So this is a laboratory problem. They're going to have one of these somewhere. They just will. So we have to, that's why we do all the labs and try to present ourselves there. So here we go. Got M plus I2 makes Mi2. Determine the molar mass of an unknown metal. A student reacts iodine with excess of the metal to form water-soluble compound Mi2, as represented by the equation above. The reaction proceeds until all the I2 is consumed. So you keep going until all the I2 is consumed. What that tells me, by the way, is that that's a perfect reaction then. You go as far as you can. The Mi2 solution is quantitatively collected, and so you're collecting it to get an amount, and heated to remove the water. And the product is dried and weighed to constant mass. Experimental steps are represented below, followed by data table. Then you got a data table. So you got a bunch of these steps. You might need them, you may not. It also depends. Different versions of the test may use different questions a little bit. Here here we go. I want to help you kind of just, this is a very common question, and it just was last year, so it's nice to see some new throwing at us. Given the metal M is in excess, so that means you reacted until you ran out of the I2, calculate the number of moles of I2 that reacted. So the I2 completely reacted. You want moles, but if you look at this table right now, all your data's in grams, right? By the way, you don't need to do this, but I'm going to number this for us in a minute, because you're going to have to tell me some things. So you don't need to number that. So I want moles. I'm probably going to need to use grams, right? I'm going to need to use my grams. So I need moles of I2. So can anybody tell me what lines I could utilize, or how am I going to find just grams of I2? The amount of I2. And I'm not trying to act like this is difficult, but it's making sure that we understand how to interpret this. Evelyn, what do you got? And you tell me with my green numbers, just so we all are on the same page. 3 minus 2 minus 1. That is overkill, but you're on the right track. If you do that, 3 minus 2 minus 1, we're going to have a negative number. Yeah, why don't you need 1? Because 2 has the beaker in it, right? Okay, so it is. It's 3 minus 2. Let's do it. Good job. What's seems a little out of place or unique already about this problem? Anybody, without me giving a huge hint, compared to most problems that we're doing on all the AP questions? Anything standing out? And literally what I just kind of wrote. What seems to be a little out of place? Now you're probably looking for such a small little thing. The way you looped your 7? Don't there seem to be a lot of sig figs? Like, oh yeah, right, oh yeah. I always just say officially, so I feel like I've said it once, be very careful when you see a problem. There's sometimes a problem, a lab problem, that will have a ton of extra digits. Usually there's only 3. There's almost always only 3. You gotta be a little careful. This could be the problem where they're testing to see if you are really understanding sig figs, and you're making sure your final answer has sig figs. So you want to make sure you mirror how many sig figs there are. Now technically I probably should have put one more 0, but when it's all said and done, because a few of these numbers only have 4, if you had 4 in any of your final answers, you're probably safe, because there are some with 5. They do a plus or minus 1. The thing is, because there was 4, unless if this is totally unused the whole time, you'll probably get away with still using 3, because they do plus or minus 1. But if you did 2, if you just sometimes short this a little bit and you get away with 2 because it's supposed to have 3, there is one problem on the test that they will penalize a point. I know it's not a big deal, but a point is a point, because of sig figs. So really push yourself to make sure that you are keeping that true with 3. If you can keep 4 on this one, that'd be ideal. So now what do? I just need to get to moles. So I will be your calculator due to time here. I want to make sure we get through a certain amount. This is only 1 point. They could have maybe done 2, but they didn't. Okay, letter B. I would have done this differently. I would have given 2 points. This one, next one, letter B, is worth 2 points, but I would have given the 2 in a different way. It says calculate the molar mass of the unknown metal. All right, these problems, if you keep straight all lab problems like this, if you keep units at the forefront of everything you're doing, you're going to have a better shot at getting it right. Molar mass is what for my unit? So those are all molar masses. Those are grams per 1 mole of everything, right? That's why they all are on the table together, because they're all comparing 1 mole. So those are I need this. If you don't have that in your head, you're not going to get this right. Oh wait, I have moles already, right? So now I need grams. Now this is interesting though. I need molar mass of M, which is weird, because I need the molar mass of M, and M means molar mass in equations, so don't get too confused. How many moles of, so I need moles and I need grams. How many moles of M do I have? Well, shoot, I don't know. Maybe I do. Maybe I don't. Here's the problem. If you look at letter A, it says M is in excess. So the amount that's there is not all that reacted. There's less that reacted. So how can I figure out how much I have of something if I have something else? Huh? How do you compare? What's the one thing we use to compare? Yes. If you have moles of something and it's asking for something else, and the moles are in any unit like that, you can always find the other one using moles because it's the perfect amount. That's what stoichiometry is. It's the perfect amount that's needed for that amount, the equal values that would consume each other. So if I have, this happens to be a 1-to-1. If it was 1-to-2, I would take the amount of I2 and I would multiply by the 2 and divide it by the 1 or whatever else I have. So this is a 1-to-1. So moles of M equals moles of I. And I'm very disappointed in this problem. I would have actually given the point for that. I think that's the harder connection to have. But they give you a point for finding grams of M, which I do not think is as difficult. What am I going to do on that? How do I find grams of M? Yep, so 2 minus 1, right? That's all I'm doing. And they give you that for the point. I still think that one's the bigger leap, personally. So, my head is in the way. So, molar mass, just put them on top of each other. One point, for some reason, is that, and 1 point is for that one. Yeah,
Isn't that not the answer? Because that's how many moles of it react.
correct. It says but it's saying calculate the molar mass, so there's excess. If I can use how much reacted because I hear what now I understand your question. I hear what you're saying. You add M, you add I2, you add water. Did I cut something off here? What does that say? What do these two things say?
Leftover M and I2.
Great, I cut off probably the most important part of my Don't cut off things, FYI. We'll come back to that. I get what you're saying. I do. Thanks.
I think you subtracted one. I got 1.72.
I agree with that.
Yes. Yes, and I was not looking closely enough. You are correct. So, let's go back to this. Cross this out or erase it. I am rushing. I'm not rushing. I'm rushing. Real bad joke. Okay. Let's bring this all together then and answer everybody's questions to show that I made a mistake, which I'm good with. Okay, here at the ending. First off, let's just talk about that for a second. Those two lines, what does that mean? After you weigh it, they heated it, and I'm sorry again, oh, that's why. You take the reaction, you have some leftover M, right? And then what you do is the solution's collected, so you only get the solution. So only this now is coming into there. Once you understand that, okay? And then you heat it, and you're left over with only Mi2. So what's in here only is the reacted M and the reacted I2. Why do you have two numbers? What does that prove? That all the water's gone, right? Like if you had a number, then another, and then they ask, well, why are you continually remassing it? And I'm assuming it's going to go down just a little bit on each of those values. Well, the water's not been all evaporated yet, so they're continually checking. So if this is the amount of M2, to be honest, I had the right answer. I just used the wrong things to subtract because I'm going way too fast. So write this down for me, please. This is totally on me. If I, like, just, this is a fruit salad and it's full of one M and 2 I's, and I remove all the I's, what's left? The M. So couldn't I just subtract how much I is in there? Where is that from? That's from up in letter A, right? So this is totally on me. Now I need to talk to mod 1. And look at that, I had the right answer. Wow. Doing it totally wrong. So it's 0.263. Just jumped into it way too hard. I hope that does make sense though. Like, okay, wait, the only thing I know about, Tyler, your first question was really great, because it's like, wait a minute, if you have just the amount of M, that then all react. But at the ending, this Mi2 is what matters. Right here, right there. Like that's all that's left. That's all that's left. That's what's being weighed at the end. So totally my fault. Let's finish up with letter C. This is where I need you to kind of get to. They do this a lot. A lot. And I want to make sure you're understanding how to answer something. It says a student hypothesizes that the compound formed in the synthesis reaction is ionic. Meaning this, by the way, that it would have something like that. Right? That would mean it's ionic. Mi2, right? Be M2 plus and I minus. C, propose an experimental test the student could perform that could be used to support the hypothesis. So first off, you need to do a test that could help prove if it's ionic. Explain how the results of the test would support the hypothesis. So after you say, I'm just going to make this up, like you drop it in water, great. Then you need to say, why does it prove it? You heat it up, great. Why does it prove it's ionic? So you need 2 parts of that. You get 1 point for explaining something that's a reasonable test. It's not like put it on a roller coaster. Like you need to have something that's actually real, and then you need to have the result of why you think that. So for example, if you wanted to prove something and you knew it precipitated, you'd say, well, you react it with another, a compound that would create a precipitate, and if a solid forms, then you know it's an insoluble compound, and you know that a precipitate would form, and you just say the results. This is a little trickier. So if I take my solid, how can I prove that it's ionic? Anybody, there's like 2 or 3 different answers you could give. But one of them you need 2 things with it. Well, right now it's like this. So you have to prove that it's this. It is a salt. Well, you're trying to prove it's a salt. I guess I don't know if it's a salt. Okay, let's start with that. So you could add to water. Because what are you hoping for? That if you add it to water, it will. Okay, add to water to dissolve. Here's the problem. That's great. That's a good start. The problem is sugar dissolves in water. And if you're like, what? Wait, it's totally salt and sugar. Very. You want to put them on your tongue? I'll let you know. Very different. We did a lab last year. We put these little things that look like computer chips, and they had a red and a green light on them. And we put them in, and they were bright or they weren't, or both lights came on or not. Anybody remember what we were testing? No, we class, I don't remember this either.
Is that hardness or like the?
Close. Yeah, oh, Morgan. Hey, you're gonna add it to water, and then this is what you have to follow up with. Test. I don't know if you ever did this in middle school. You ever put a light bulb in different solutions and the ones that lit up? And if you didn't, I'm telling you now, if you put it in salt water, the light bulb lights up. If you put it in like sugar water or something that doesn't dissolve, the light bulb won't light up. And we had 2 open lines, and the electrical current runs through those charges that are dissolved. And if there's no charges dissolved in the water, the current won't pass through. So you have to have connectivity. Here's one other one. Because salts, remember salts. Don't ever forget this, by the way. Keep this at the forefront for salts. What does that mean? They're really attracted to each other, right? So what if you heated it? What if you tested its melting point or its boiling point? Would it have a high, like, and I know it's relative. Everything when you say high or low, I know we're at time, but we're almost done here. Would it have a high or a low melting or boiling point if it was ionic versus covalent? Anyone know? Low? The greater with our charges, the more attracted they are. Just remember this, that lattice energy that we always did with that Born-Haber, that was a huge number, wasn't it? It was like mammoth. That number reflects how strong I am. So, the higher it is, more ionic it is. Ionic is the strongest. God, I'm breaking everything. So you understand, 1 point is earned for the appropriate test. So if you just had some sort of a test, so you could have tested for a boiling or melting point, or if it dissolves with conductivity, and then 1 point explains the result. So the result would have been, if it's high, it's ionic. The result would have been, if it's high conductivity, it proves that it's ionic. That'd be the other point. Please, tomorrow, I am stamping problem 1, a single chapter 7 and a single chapter 9 sheet, okay? So be working on those two. I sent you a thing in Canvas of everything that's due and when. And AP format 1 and 2 are due by the end of the day. Thank you, guys.